Hello class, back again. Now we're going to talk about bond order, bond energy, and bond length. Three interrelated concepts. Imagine if you have two atoms, let's say two carbon atoms. If you have two atoms and if they're bonded together by either one bond or two bonds or three bonds, you can imagine these as either being rubber bands or springs. It's pretty intuitive that if you have three of these bonds or rubber bands or springs tying together the two atoms, that this will hold those two atoms closer together. They'll have a shorter bond length. And also, it would be more difficult. It would take more energy. It would drain more from your lightsaber if you tried to cut through or break a triple bond as compared to a single bond. And likewise, if you had two rubber bands or two springs holding together atoms, that is a double bond, it will be intermediate between a triple bond and a single bond. Basically, those are the concepts of bond order, bond energy, and bond length. And we're going to put some skin on this by showing you some tables and some numbers. So this slide shows a table of bond order, bond length or bond distance, and average bond dissociation energy or average bond energy for carbon-oxygen bonds, carbon-carbon bonds, and nitrogen-nitrogen bonds, in which you have the series of a single bond between carbon and oxygen, a double bond between carbon and oxygen, and a triple bond. Likewise, a single bond between carbon and carbon, a double bond, a triple bond. You're comparing the series, and likewise comparing a single, double, and triple bond between two nitrogen atoms. Bond orders 1, 2, 3 in each of these cases. As you can see, the bond length gets shorter as you go from a triple bond to a single bond between the two atoms. This holds for each case, carbon-oxygen, carbon-carbon, nitrogen-nitrogen. And the bond energy, the energy needed to break those bonds, gets larger as you go from a single to a triple bond. Sometimes I'll refer to this average bond energy as BE, and sometimes I'll call it a bond dissociation energy and give it either a symbol of D, capital D, for dissociation, or delta H with a little subscript D, again for dissociation. And it's the energy needed to break the bond. Now, it will always take energy, it'll be an endothermic process, to break a bond. A formula that we will use in another slide or two is shown on the bottom left of this slide, where you can estimate the enthalpy change for a reaction, that's delta H subscript RXN, by adding together the bond dissociation energies of those bonds that have to be broken from the reactants, and then subtracted that the sum of the bond dissociation energies of all those bonds that are formed in the products. That is, you're breaking bonds of the reactants and you're forming, that's why there's a negative sign, you're forming bonds of the products. Let me point out that you'll have a table of this sort in a textbook, or you can Google average bond dissociation energies and get tables of this sort. And these tend to be average values that have been determined for a set of molecules and then sort of averaged to put a number in a table. Also, they tend to refer to the bond length and bond dissociation energy in the gas phase. That'll be a little bit important, perhaps. Well, let's now talk about how we use these concepts of bond order, bond energy, and bond length. A couple of uses are in the next two slides. One use is to analyze potential resonance forms of a molecule or a polyatomic species, and for us to use these concepts to try to help us understand the chemistry of these species. Let's consider carbonate, CO3-2. We use this as an example species in learning how to draw Lewis dot structures. You may recall we wound up with a Lewis structure as shown perhaps in the middle, where you had carbon in the center of this polyatomic species. You had sigma bonds to the three oxygens, but in one case, to one of the oxygens, there was a double bond. And remember, we had to take a non-bonded pair down and convert it to a pi bond in order to satisfy the octet rule for the central carbon. Remember that? We also at that time mentioned that the position of the carbon-oxygen double bond was fleeting. It could be between carbon and any of the three oxygens. And we said that this is an example of what are called resonance forms, that all three forms actually exist and interconvert very, very rapidly, so that the position of the carbon-oxygen double bond is not really fixed. It's fleeting between the three different positions. With that in mind, what if I were to ask the question, what is the average bond order of a carbon-oxygen bond in carbonate? Let's think about that for a second. If we take any one of these particular resonance forms and focus on it, you have one carbon-oxygen bond, which is bond order 2, a double bond, and the other two are bond order 1, a single bond. So if you were to average 2 and 1 and 1, take the average of those three numbers, just plug them in your calculator, and of course what you get is 4/3. So we would say that the average bond order for the carbon-oxygen bond in carbonate is 4/3. That is, we average the bond order for the three carbon-oxygen bonds for the three positions to come up with 4/3. Imagine for a second carbon dioxide with carbon in the middle and two terminal oxygens, and as you recall, there's a double bond between the central carbon and each of the oxygens. Each of those carbon-oxygen bonds is bond order 2. It's a double bond. If you were asked what is the average carbon-oxygen bond order in carbon dioxide, you would say 2 plus 2 divided by 2, 2. The average is 2. Okay, now let's return to carbonate. We said that the average bond order is 4/3. What might this mean? You would then imagine that if the average bond order is 4/3 and the position of the double bond is actually fleeting between the three different positions, that the carbon-oxygen bonds would have properties that are in between a carbon-oxygen double bond and a carbon-oxygen single bond. That is, you would expect the average bond length of a carbon-oxygen bond in carbonate to be in between that for a carbon-oxygen double bond and a carbon-oxygen single bond. And, in fact, that is what is found. In the little table to the right, I again show you the values for the bond length of a carbon-oxygen single bond, a carbon-oxygen double bond, and a carbon-oxygen triple bond. 143 picometers, 122 picometers, and 113 picometers. I think I forgot to mention that these are measured in terms of what we call picometers, 10 to the minus 12 meters. Anyway, these are the known bond lengths for a carbon-oxygen single, double, and triple bond. Well, for carbonate, it can be experimentally determined using methods such as X-ray crystallography, which we'll get to sometime later in this course. It can be determined that the average bond length between a carbon and oxygen carbonate is 129 picometers. Now, look at the table. Does that make sense? And yes, it does. It's in between the carbon-oxygen single bond value and the carbon-oxygen double bond value. Another use of the concepts of bond order, bond energy, and bond length is to estimate the enthalpy change for a reaction. To do this, we have to have a handy table of bond association energies. We have to have the balanced reaction, and we have to draw out the Lewis dot structures for the reactants and products. And I've done this in this example of nitrogen plus 2 fluorines going to dinitrogen tetrafluoride. That's the reaction. I've drawn out the Lewis dot structures showing that diatomic nitrogen has a triple bond between the two nitrogens. Diatomic fluorine has only a single bond, bond order 1. And in dinitrogen tetrafluoride, by drawing out the Lewis dot structure, following the procedures that we've discussed earlier, this molecule has a nitrogen-nitrogen single bond. That is, there's a single bond, or bond order 1, between the two nitrogen atoms. And between the nitrogen atoms and each of the fluorines, there's also a single bond, or bond order 1, for the nitrogen-fluorine bonds, of which there are 4. So, to estimate the enthalpy change for this reaction, you add up the enthalpy change for breaking a nitrogen-nitrogen triple bond. Again, imagine you have your lightsaber out and you're determining how much energy is required to slice through that nitrogen-nitrogen triple bond. That turns out to be 946 kilojoules. That's a unit of measure of energy, of course, kilojoules. Plus 2 times 159 kilojoules, the energy required to break a fluorine-fluorine bond. Why 2? Because if you notice the stoichiometry in this balanced reaction, I'm doing this for 2 diatomic fluorines. I didn't draw the other one, but it's there. So I have to add the bond association energies for breaking the bonds in the reactants, and then I have to subtract, notice the minus sign in the parentheses, I have to subtract the bond association energies for breaking a nitrogen-nitrogen single bond, that's 163 kilojoules, and 4 times the bond dissociation energy for breaking a nitrogen-fluorine bond. 4 because there are 4 nitrogen-fluorine bonds in this molecule. Now again, all these numbers will be in a table that you can find in the book. But when I add the bond dissociation energies for the reactants minus the bond dissociation energy for the products, multiplying by how many bonds that I have to break or make in each case, I then add that all up to get the delta H of the reaction. And in this case, it turns out to be 13 kilojoules. Now the last concept I want to go over in this chapter is polar covalent bonds. We've discussed covalent bonds as if there's a perfect sharing of the pair of electrons between two atoms. And in fact, that's not the way it works in many cases. And that's because different elements have different electronegativities. Fluorine and oxygen, for example, are the most electronegative of the elements. They are the electron hogs. And if any other atom forms a bond to oxygen or fluorine, the electrons for that covalent bond really spend most of their time around the more electronegative atom. And let me give you a couple of examples here. Hydrogen fluoride and water. For hydrogen fluoride, fluorine is the most electronegative atom. So when it forms a covalent bond with a hydrogen atom, the fluorine will pull the lion's share, most of the electrons, around itself, leaving the hydrogen mostly bare of an electron cloud. We have different ways to represent that. One is to use these little delta minus and delta pluses symbols, indicating that there's an excess of electron density, meaning that the electrons spend most of their time around one atom, and we indicate that by a little delta minus. Delta means a little bit or partially negatively charged. And that the other atom, the hydrogen atom in this case, is deficient of the electrons swarming around it. So we refer to that as a delta plus. It's partially positively charged. So one way is to put the little delta pluses and delta minuses. Another way is by using arrows where you have one end of the arrow has a plus sign for partially positive and the other end of the arrow is the pointy part of the arrow. That's just a convention. So the point is that many covalent bonds are actually what we call polar covalent bonds. Even though covalent bonding involves sharing, they are not shared equally when you're dealing with one of the more electronegative elements. The next example, let's talk about water. Here again, we have hydrogen, poor little hydrogen, sharing 2 electrons with oxygen, an electronegative element, and the oxygen will actually pull most of the electrons of those sigma bonds, those covalent bonds, around itself, with the oxygen being partially negative and the 2 hydrogen atoms being deficient of electron clouds and be partially positive. And this would be a way to represent that. Now, as I say in this slide, spoiler alert, because in the very next set of lessons, we'll learn that water is actually not a linear molecule as I've drawn it here. It's actually a bent molecule, and that will have additional ramifications. So let's stop now that we've learned about polar covalent bonds.